Okay, welcome to part 3. Okay, and suppose that a manufacturer is testing one of its machines to make sure that the machine is producing more than 97% good parts. And you can see here, this is the hypothesis, right? The test results in a p-value of 0.122. Now, this is kind of significant, right? Because 0.122 is probably greater than alpha. Okay? Unknown to the manufacturer, the machine is actually producing 99% good parts. So, actually, the alternative hypothesis is true, right? Um, so, here, though, right? So so the alternative hypothesis is true, okay? So the null hypothesis is false, all right? Here, though, with such a large p-value, what we're going to do is fail to reject, right? So we're going to fail to reject. Now, we're talking about types of errors, right? What have I always told you? Like 18 times. I don't do any type of error testing unless I draw my chart, right? So H naught is true, H naught is false. Ooh, that's a terrible F. Let's fix that. Okay. Fix it. All right. False. Okay. And so we reject and we fail to reject. Now, of course, this is a type 1 error. This is a correct assumption. This is a correct assumption. And then this is a type 2 error. Okay, so I have told you that H naught is false and that we failed to reject, right? And so if I look here, H naught being false, right, and we failed to reject is a type 2 error, right? It's right there in the chart. So what we're going to do is fail to reject, making a type 2 error. And see how that works? Okay. I don't really need to go through the rest of these. You can probably see why they're wrong, seeing why this is the correct answer. Okay? Alright, so 11. Placebos are a tool for blinding. Okay? We're not sampling with placebos. It's not a sampling method. Okay? Placebos aren't randomization. We randomize and then we assign the placebo. Okay? Placebos can sort of be a tool for control, right? But the control group usually doesn't take anything. Okay? So you're controlling a little bit for the placebo effect, but this is not the best answer, okay? So this is not the best. And with multiple choice, you're always looking for the best answer. The placebo really blinds the participant to the fact that he's not actually getting the treatment and prevents biasing, okay? And then blocking is a sampling technique, so this isn't going to be true. So while I can see that D looks sort of correct, right? It's really not the best answer because the purpose of a placebo is to blind the participant to the fact that they're not actually getting their treatment to reduce bias. Control is to help us compare one sample to another, and that's not really what placebos are for. That's what like the randomization, random assignment and stuff are for. Okay? So B is going to be the best answer here. B. Best answer. D, not the best answer. All right. 12. A pharmaceutical company investigating whether drugstores are less likely than food stores to remove over-the-counter drugs from the shelves when the drugs are past the expiration date found a p-value of, well, I would rather report p, right? Not as a percentage, but as an actual, there we go, probability. Okay. Now, do we remember what p-value means? P-value means seeing a sample this far, right? Given, right, the probability of seeing a sample this far, given the null is true, right? We assume that the null is true to get this probability. So what we're looking for is something that tells us that seeing drugstores, right, with a removal rate this far, right, from probably no difference. So that's what we're looking for. We're looking for that a difference this large in the drugstores would be this likely right here, given that there's no difference. So 2.8% more drugstores removed. Oh, this more drugstores right here, that doesn't really, p-values don't tell us how much more. Confidence intervals tell us a little bit of something about more, but not p-values. So A is not good. There's a 2.8% chance the drugstores remove more expired over-the-counter products. Yeah, so this one's a little tricky. There is a 2.8% chance, okay? And we are talking about drugstores removing their expired over-the-counter products, but there's some verbiage that's missing here, right? It's not actually that there's a 2% chance that the drugstores remove more, okay? It's a 2.8% chance that there is a no difference given what we observed, right? Assuming that the null hypothesis is true. And in fact, with such a small p-value, we would probably say that the drugstores do remove more expired over-the-counter products, right, than food stores. And so this 2.8% chance is really the inverse statement here, and so this is not going to be true, okay? Not going to be true. And I could see how it would be a little tricky. I don't know. I haven't marked out any of these, so C is still a possibility. 97.2% more drugstores removed. Oh, more drugstores? P-values don't tell us about more drugstores. They just tell us about how far apart the means or the proportions are. So this more drugstores thing is bad language. Okay, we don't want to do that. There's a 97.2% chance the drugstores remove more expired over-the-counter drugs. And again, this is one of those places where, you know, probability is a chance. We are talking about drugstores removing more expired products. What's missing here is given no difference, right? Given we assume no difference, then yeah. So this language again is just very difficult. It leaves out some assumptions that we need, and so E is not going to be the right answer here. And I could see how with B and C, right? With B and E, with B and E, with the chance and the drugstores removing, and we're thinking, yeah, the drugstores probably are removing more, but that's because our p-value is really low. All right, so we would observe the drugstores removing at this rate given no difference. Okay, and so B and E are both going to be incorrect. All right, and so it's going to be C. None of these is the correct answer. All right, and hopefully my language wasn't too convoluted. But this is not the way we write, right? B and E are not the way we write conclusions, right? And these are sort of conclusions here. And this is not how we write our conclusions. Not how we write conclusions. right? So that's why I don't like B and E, because they're really not like how we write a conclusions. Okay, and I think that's pretty straightforward. Okay, so let's go on to 13. We'll do 13 and 14 because the video is getting kind of long, and then we'll finish up this page. So the investigators at an agricultural research facility randomly assigned equal numbers of chickens to be housed. In one room, a group of chickens experienced normal day-night, while the other room, the lights were left on 24 hours. After collecting data for several days, they tested the hypothesis. So the null hypothesis is the light made no difference in the egg laying against the one-tail alternative. All right, now let's actually write that, right? So our alternative hypothesis would be that mu1 minus mu2. Okay, now while the other room were left on to see if chickens would lay more eggs. All right, so I think what we're assuming is that the two are going to lay more eggs, right? The second group is going to lay more eggs. If the second group lays more eggs, this is a bigger negative number, so my value should be negative, and I'm going to test it against this. We found that P is 0.22. Well, 0.22 is pretty much always greater than alpha. And so here we're going to fail to reject. Okay? And so we're looking for some sort of a correctly written conclusion for 13. All right? There is a 22% chance that chickens housed in lighted rooms produce more eggs. Well, that's not what that means, okay? There's a 22% chance that we would observe this difference in means, given the null hypothesis is true. The chickens in the lighted room averaged, more eggs per day? No, bad language. So B is totally out. There's a 22% chance that there's really no difference in egg production. Again, this is one of those things where you would think, well, yeah, there's this, but it's not. It's not a 22% chance that there's really no difference. That's a pretty small chance. We're actually saying that we're going to fail to reject this at this level because this second sample was really not that far away. Okay, so that's not really what these mean. Okay, and so there's a 22% chance another experiment will give the same results. How can we compare? I mean, we can compare experiments, but this experiment is not a predictor of what other experiments will come up with. That's not what a p-value means. Okay, we might interpret that way, but that's not what a p-value means. And so now we are left again with none of these, and really, again, this is not how we write conclusions. Okay? And so because this is not how we write conclusions, wow, of course, this is not how we write so that people can read it either. This is not how we write conclusions, okay? And so this is why this one is none of the above. All right, last one on this page. We're about to test a hypothesis using data from a well-designed study. So a well-designed study just means we meet all of the assumptions, okay, so that this is appropriate, which is true. A small p-value would be strong evidence against the null hypothesis. Yeah, right? If you have a small p-value, you would tend to reject the null hypothesis, and rejecting the null hypothesis is evidence against. We set a higher standard of proof by choosing 10 instead of 5. Now, we talked about this. This is really opposite. Okay? You choose a higher standard of proof by choosing a smaller alpha. That's a higher standard of proof. Okay? So this one is going to be wrong. Okay? If we reduce the alpha, we reduce the power of the test. And that is true. These things are connected. Okay? So this is true. These things are connected. As alpha gets smaller, the power of the test gets smaller because alpha and power are directly related. Okay, and that makes us happy. So that means that the answer here is 1 and 3. And so 1 and 3 is E only. Okay. Now let's conclude this video because this has been really long. And I will see you all in part 4.